How you doing? Good. How are you? Doing good. Okay, it is 6:02, so let's go ahead and get started. Y'all ready to go?
Record lectures right now on YouTube. Don't forget that last week we did the day of the test because it was scheduled Labor Day.
Yes.
That's the hard one. One easy definition is it splits the data set into two parts, one that's below that percentage, one that's above that cutoff or that percentage, I guess. So if you're looking at the 10th percentile, then you are, 10% falls below, 90% is above. So it splits the data set into two parts where a certain percentage is below, and then the inverse of that is above. So long story short, splits the data set into two parts based on what percentile you're interested in. All right, so the thing we did not get to talk about was measures of dispersion. The things we did not get to talk about were measures of dispersion. So in addition to knowing where the center of our data is, so that was measures of central tendency, it's also important to know how spread apart our data is. It's also important to know how spread apart our data is. So in addition to knowing generally, is our data, in addition to knowing in general, is our data, is the center right here versus right here. It's also important to know, well, is our data spread out like this? Or is it spread out more like this? And that's what we get at with measures of dispersion. That's what we get at with measures of dispersion. So central tendency is all about where the center of our data is. Measures of dispersion, it's all about how spread apart our data is. It's all about how spread apart our data is. Okay. So from knowing the central tendency and from knowing the dispersion of our data, we can get a decent sense of what our data looks like without even needing to chart it or without even needing to graph it. If we just know the mean and the standard deviation, for example, we get a good feel for what our data looks like. What is the shape? And by the end of today's lecture, you will be able to do that too. By the end of today's lecture, if I give you a mean and a standard deviation, you can instantly know, hey, we're looking at a population that looks like this, or maybe a sample that looks like this, or maybe even our data is totally messed up. We need to go back to the drawing board. We messed up somewhere. So by the end of the day, you will hopefully be able to figure that out. Okay, so the first one we're going to talk about is range. So range is the simplest measure of dispersion. So range is simply your maximum value subtracted by your minimum value. So range is simply your maximum value subtracted by your minimum value. So in this example, we might have a max value of 20. We might have a minimum of 1. So for that distribution right there, what would be the range? Say it louder. Yep, 19, 19. So for this distribution right here, we take the max minus the min, and that's 19. That would be 19. But then for this one right here, let's say it is 7 and 3. What would be the range for that one? 4, that's correct. So this one would be 4, this one is 19. So that's the range. It doesn't really help out all that much in practice or in research. And the main reason for that is it's really hard to tell are all your values spread apart, or is it just one? So for example, you could have something that looks like this, and that would have a range of 6. Our biggest value is 7, our smallest is 1, and that's a range of 6. We might have something like this. Once again, largest of 7, smallest of 1, we have a range of 6. Or we might have something where we have a single outlier that throws everything off, and we have one value of 7, all these over here with the smallest being a 1, and once again, we have a range of 6. So in all 3 of those examples, we have the same range, even though the shapes of that data, even though the dispersion of that data was very, very different. So therefore, our range doesn't help us all that much. We have to look at other measures of dispersion. So the other measures of dispersion we're going to talk about are the most popular ones by far, and they're variance and standard deviation. Variance and standard deviation. So variance just measures how far each value in the data set is from the mean on average. So variance is just how far each number is from the data set from the mean on average. And if you have a full data set full of a bunch of different variables, you can calculate a variance value for each of them. So if we have a data set with something like this, we have a data set that looks like we have a job performance score, we have a job satisfaction score, we have an employee engagement score, and we have participants' values like this. 1, 2, 1. We can calculate a variance score for each of these variables. So maybe job performance's variance score is 1, job satisfaction variance score is 2, and then employee engagement might be 1.5. So very similar to mean, median, and mode in that regard, is that each variable in your data set, you can calculate a variance score. It's a characteristic of the variable. The characteristic of that variable right there. Any questions about that so far? Is that pretty clear? Okay. So also statistically, your variance is the average of the squared differences between the observations and the mean. So it's the average of the squared differences between the observations and the mean. So if you have the mean right here, conceptually, it looks like this, where you would take each of these distances, like this for each value. You would square them. So this little 2 is supposed to be squared. And then you sum them together. And then you sum them together. So conceptually, that's what it is. I don't expect you to know that. That's not going to be on the test. But conceptually and statistically, mathematically, what the variance is the average of the squared differences between the observation and the mean. So if this is a mean of 5, and this is 1, 2, and 4, the difference with this would be 4. So it would be 4 squared. The difference with this would be 3, so 3 squared, and the difference between this and the mean would be 1, so it's 1 squared. You take all of those, and then if you get it over here too, you would add them up, and then divide by the total number, and it would give you your variance. So that might help some people, that might make things more confusing. If it makes things more confusing, just forget that. Just throw that out your mind. The important thing I want you to know is that the standard deviation also measures how far each number is from the mean on average. So it also is a measure how far each number is from the mean on average. And once again, each measured variable within a data set will have one standard deviation value. So just like we could take the variance of job performance, the variance of job satisfaction, the variance of employee engagement, we can also take the you can also get the standard deviation of job performance. You can get the standard deviation of job satisfaction. And we could get the standard deviation of employee engagement. So once again, like we could calculate the variance for each of these, we could also calculate the standard deviation for each of these. So the standard deviation, the difference between the two, is the variance value. It's very hard to interpret. I think this is the next slide. Don't want to talk about that now. So first off, standard deviation is the most popular measure of dispersion. All right, yeah, let's go ahead and talk about that. All right, so standard deviation is the most popular measure of dispersion because the variance value is hard to interpret. Your variance is very hard to interpret. However, once you take your variance and take the square root of it, that transforms it into a standard deviation. So taking the square root of your variance transforms it into your standard deviation. And the standard deviation is much more interpretable. The standard deviation is much more interpretable. So whereas in variance is hard to interpret, the standard deviation takes your measure of dispersion and puts it back into the units of the original variable. It takes your measure of dispersion and puts it back into the units of the original variable. And I know that's confusing right now, but in a few minutes we'll go through some examples, and hopefully it will click a little bit for you. Hopefully it will click. But as of right now, just remember, they both, variance and standard deviation, are measures of dispersion. Both variance and standard deviation are measures of dispersion. Standard deviation is much more popular. Standard deviation is much more popular. And standard deviation is in the units of your original variable. Standard deviation is in the units of your original variable. So a variance is hard to interpret because it's not in the same unit as the original variable. Standard deviation is much more easy to interpret because it is in the units of your original variable. And that might not click right now, that's perfectly fine. Hopefully by the end of today's lecture, things will start to make sense by the end of it. But as of right now, let that settle in your mind. Okay, so these are the formulas. So as you can see, the variance is exactly what we talked about before. So the first part, let's go through it piece by piece. So what's that symbol right there mean?
Summation.
Yep, summation. So it's the sum of. So sigma, sum of. The next one is x of I. So what is x of I? Say it again. Yeah, so each observation of your variable, so each observation of your initial variable, so we have sum of each observation of your initial variable, but then we also have this right here. We have x bar. We learned that last class. What is x bar? Yep, good job. It is the mean. And then we have this 2 right here. So what is the 2? Yep, it means squared, exactly. So the top half of that is simply the sum of each of your observations minus the mean squared. So you would take each of your observations, subtract the mean, square it, and then sum all of them. And that's exactly what we did right here. That is 100% what we did right here. This right here just represents each observation, the distance from the mean, so subtract the mean, square it, and then sum all of them together. And then sum all of them together. But then the little last part is the n minus 1. So what is n? Yeah, number of observations, your sample size. So number of observations. So this is just pretty much getting the mean, or getting us to the average distance from the mean. It's getting us to the average distance from the mean. So in short, sigma, sum of each observation minus the mean squared divided by the number of observations subtracted by 1. So exactly what we talked about here, just putting it out mathematically. So taking this right here and putting it mathematically. Standard deviation is much easier. Standard deviation is much easier. Standard deviation is simply s squared, you take the square root of it. So whereas this was variance, this is standard deviation. So what is s squared? What is s squared? There you go, variance. Yep, s squared is the variance, and we see that up there. So while this formula is complex and for variance, this one is easy. It's just your square root of the variance. So to get your standard deviation, mathematically, you first have to get the variance and then take the square root of the variance. Fortunately, every stats program ever, you can just directly calculate the standard deviation. So every stats program ever, you can just directly calculate the standard deviation. You don't have to do this first to get to here. Every stats program will just let you jump straight to the standard deviation. Okay. Don't want to talk about coefficient of variation. Let's skip coefficient of variation. Coefficient of variation will not be on a test, so surprise. Okay. Any questions about that? Any questions? Yes.
So on the test, we'll be expected to do this by hand, or will we be able to something more?
Good question. So on the test, you will have, it's going to be on a computer, so I will have no idea if you use a stats program. So therefore, you're allowed to use one. Yeah. You are allowed to use stats programs. Yep. So from this slide, I would expect you to, if I gave you those two formulas, to be able to, and I said, pick out the 4 most important parts, to tell me what the 4 most important parts are, such as sigma, x of I, x bar, what are those? And then it would be realistic for me to give you a data set and say, calculate the standard deviation. Yep. And I would heavily encourage you, if that was a question, to use a stats program. Yep, I would not want you to do all that by hand. So, any other questions? Any other questions at all? Okay. All right, so we talked about all of that to eventually get to the normal distribution. We're going to talk about this a lot today. We're going to talk about the normal distribution a lot today. So normal distribution is if we assume that our data has a certain shape, just based on our mean and standard deviation, we can get an estimate for where our values fall. So you can have a lot of different assumptions about the shape of your data. You can assume a logarithmic distribution, you can assume a Poisson distribution, but the most common is the normal distribution. The most common assumption about the shape of your data is the normal distribution. And that's what we're going to start by talking about. Okay, so the normal distribution looks like this. So eventually we will look at this and you'll see it and think, oh, I know exactly what that means. That's going to click really quickly for you by the end of the semester. But instead, let's start with this more simple version. This is the more simple version of the standard distribution. So as you see the standard distribution, if you assume your data has this shape, your mean falls right in the dead center. So that, I believe it's called a mu. So this symbol right here, for those who know, is that a mu? Yeah, okay, good. I'll wait on that. Good job. Okay, so yeah, so that is your mean right there. So the thing that falls in the center, that is your mean. If you look at the left and the right of the mean, your standard normal distribution assumes that 68.2% of your data falls within one standard deviation of your mean. So the normal distribution assumes that 68.2% of your data falls within one standard deviation of your mean. So what this means is that if we assume a normal distribution, we have the middle right here. And if we know the mean is something like a 5, and we have a standard deviation of 1, if we were to then go one standard deviation below the mean, which would be 4, and one standard deviation above the mean, which would be 6, and we're just interested in all the observations that fall right here, we assume a normal distribution, that's going to be 68.2% of our data. That's going to be 68.2% of our data if we're assuming a normal distribution. Then if we go one more step out, then we want to look at 2 standard deviations away from the mean. And now we're looking at 2 standard deviations away from the mean. We have a mean of 5 and a standard deviation of 1. That'll be 3 and 7. And we look at 2 standard deviations away from the mean. That's going to represent 95.4% of our data. That's going to represent 95.4% of our data. And then the last one that we'll talk about is that we go 3 standard deviations out, which is a whole lot of data. That represents most of our data. So in this case, it would be from 2 to 8. That's going to represent 99.7% of our data. That's going to represent 99.7% of our data. So the normal distribution just says we have a bell-shaped our data to assume a normal distribution. It says the percentages of our data fall within these exact boundaries. It's roughly 68% falls within one standard deviation, roughly 95% falls within 2 standard deviations, and then roughly 90.7% of our data falls within 3 standard deviations. So therefore, if you're assuming a normal distribution with your data, just from knowing the mean and standard deviation, you can get a good estimate of where most of your values fall. You can get a really good estimate for where most of your values fall. Well, why is that important? We just now covered that with 5 and 1. So why is that important? First off, a lot of our statistics assume a normal distribution. So if you're running a correlation, a regression, a t-test, and ANOVA, a lot of them assume that your data has this normal shape. So that's good if your data does fall within a normal distribution. That's wonderful. Your analyses are going to be accurate. You're going to get accurate results. But if your data doesn't fall within this normal distribution, you can have biases in your results. You can have error in your results. So a lot of our analyses assume a normal distribution. So if your data follows a normal distribution, good, great, grand, wonderful. But if your data does not follow a normal distribution, you could get errors in your results. You could have biases in your results. Also, though, another reason why we should know this is in practice, a lot of our data generally falls within this distribution. So in practice, a lot of data does fall within this distribution. People's height is relatively normal. People's weight is relatively normal, things like that. A lot of things in the natural world follow a normal distribution, but not everything, So keep that in mind as we go through the semester, is that a lot of things do follow a normal distribution, but not everything. And actually, once we get to the nitty-gritty, a few things follow it perfectly. So we will talk about that more throughout the semester. Okay. So then based on this, let's say we are assuming a normal distribution. Just knowing how this functions the shape of your data, you can then generally understand, well, what type of participants are we talking about with knowing very little about them? You can get a good idea of what your participants are like when knowing very little about them. So to start, let's say we're talking about age. So let's say we're talking about age, and we have a sample, and we know that we're going to assume a normal distribution, and we know that their average age is 20 with a standard deviation of 1. So first off, where would we assume 95% of our values to fall in regards to age in our data set? So what age would we expect 95% of our participants to have in our data set? Sorry, someone say that again? Yeah, 18 to 22. Okay, I thought I heard 18.22. Okay, yes, 18 to 22. That is correct. We'd expect 95 of our participants to have a age range, or sorry, have an age between 18 and 22. So the mean of 20 minus 2 plus 2, 18 to 20. Does this work? Is this working? Okay, now it's working. Okay, so now that people can hear again, I'm not assuming that was a Zoom problem. I'm just going to leave this up. All right, so now we talked about that, mean of 20, standard deviation of 1. So let's talk about the next example. Okay, so now we have, let's say, a sample with a mean of 70 and a standard deviation of 10 for age. So first off, where would we expect 95% of the values to fall? Yep, that's correct, between 50 and 90. Because we have an average of 70. So 2 standard deviations below, it would be 50, 2 above would be 90. So if someone gave us a data set of that, what would we think about it? Yeah, exactly. Older people, retired people, retirees, possibly. So we would know that we have an unusual sample. It might be retirees, not really working age people anymore. Some of them will be, but we're looking at people with a mean age of 70 and some above. All right, so next one, let's say it had a mean age of 45 with a standard deviation of 10. So where would 95% of those values fall? Yep, 25 and 65. So we would expect 25 to 65. And then what would we say about that sample? Someone gave us a data set with this age distribution. Exactly, working age adults. We probably are looking at working age adults. So if I'm a researcher and someone says, hey, I have a great data set for you to study these employees, and I saw a mean age of 45 and a standard deviation of 10, I'd be okay with that. I would say, all right, it seems like you have working age adults. Cool. All right. And here's another example. Let's say we have a mean of 45 and a standard deviation of 100. So what would we expect 95% of our data to fall? Negative 155 to 245. So if someone gave us a data set where that would be what we expect with the normal distribution, what would we think about that? Exactly. Probably something messed up. Probably something messed up. If we saw where the mean age was 45 and a standard deviation is something so unreasonable that a normal distribution wouldn't even come close to fitting, then there might be a mistake there. Sometimes you could get instances where it might go a little bit above, and that's usually when your data might have a shape like kind of shape like that. Sometimes that can give you weird standard deviations where it could be a little bit above what you'd expect. So it might be, to use a 70 example, something like this might have a mean of 70 and a standard deviation of, let's say 20. So let's say mean 70, standard deviation of 20. So if we did that, that would go from about 30 to 110. 110 would be a little bit unreasonable, but that's like barely there, so maybe that could work. So maybe a mean of 70 and a standard deviation of 20 could maybe work. But once you're getting to something like a mean of 45 for each or the standard deviation of 100, and it's insinuating that 95% of your data falls within negative 165, positive 245, then that's just crazy. That's just unreasonable. So you have a mistake somewhere in your data set. And if we're talking about is it working now? Okay. Apparently that's the way you fix it for some reason. Okay, so to continue, let's talk about grades briefly. So if we have a class, or let's say you have a friend who's in a class, and they say, oh, this class is so great, we have a mean grade of 95 with a standard deviation of 5. What would you think about that? Exactly, easy course, easy course. Then yeah, if we did the distribution thing, that would go a little bit above 100, but it's kind of like this example, it's probably skewed data, so your standard deviation doesn't fit the normal distribution perfectly. So this is an example of if your data doesn't follow a normal distribution perfectly, then some things like that will happen where even though the max grade might be 100, it would insinuate that there's some people outside of this boundary. But once you get used to it, once you learn more about it, you can recognize, all right, so that mean is high, the standard deviation is 5. That's an easy class. That's an easy class. That's a super easy class. All right, what about a friend who said this class has a mean of 85 with a standard deviation of 5? What would you think about that? About average, yeah, that's probably average. That's a normal class. If it's a normal distribution, that would be good. So therefore, this is a normal class. And if you had a friend who said their class has a mean of 75 with a standard deviation of 5, would you take that class? Probably not. Probably don't want to. That's going to be a tough one. That's going to be a tough one. Okay. So let's talk about employee salaries quickly. So the first one is mean of 50,000, standard deviation of 10,000. So what type of job would that be? So maybe lower tier, about average. Yeah, about average out of undergrad maybe. But then if we had a sample of employees and their average income was 125,000 with the standard deviation of 25,000, what type of employees would this be? Yeah, managers, probably looking at managers, level employees. What if they had a mean of 12,000 with a standard deviation of 0?
Interns.
Exactly, probably interns and maybe grad students. You have some type of sample where, and this is important to note. Is this working as it appears to me? Y'all did hear my mic go off just now, right? Yeah. Can y'all hear me now? Are y'all saying yes? Yes, you can hear me? All right, what do y'all think? Can they hear me? Okay, no, okay, they're saying yes now. Okay. I'm assuming this is Zoom problems. In case y'all haven't seen, Zoom is having national outages. My wife had to teach on Zoom today, and her entire class, it just wouldn't let her log in for most of the time. So hopefully once classes start across the nation, Zoom will get its act in order, or whatever happens. Okay. All right, so that's all I wanted to note about standard deviation. Do y'all have any questions about it? Any comments about standard deviation? Okay. We will come back to standard deviation throughout the semester. That is an extremely important statistical topic, extremely important. So we will talk about it all throughout the semester. All right, so another thing we should know about is z-scores. So we should talk about z-scores very briefly. And a z-score tells you how many standard deviations a value is from the mean. So a z-score is how many standard deviations a value is from the mean. So first of all, this is different than variance and standard deviation. So this is different than variance and standard deviation, whereas variance and standard deviation was only represented variables, whereas variance and standard deviation only applied to variables. You can calculate a z-score for every single person in your data set, for every single variable. So you can calculate a z-score for every single observation you have in your data set, so for every person, for every variable. In your z-score for each person that you calculated for, tells you the number of standard deviations a value is from the mean. Number of standard deviations a value is from the mean. So let's say in this example, we had a person that got a 5 on this, whatever we're measuring, let's say job satisfaction, they have a score of 5. We could take this, calculate a z-score, and that might say 1. So we take this 5, calculate a z-score, the z-score is 1. So what would that tell us? If the z-score was 1. Yep, so the 1 standard deviation from the mean. So this would say that this person, if we're looking at job satisfaction, and their z-score is 1, that they were 1 standard deviation above the mean regarding their job satisfaction. So if we're looking at these distribution ranges, I have this on the next page. All right, so if we're looking at this, we see that we can look at the different distributions, and we can calculate, well, how many people, based on their z-score, if we're assuming a normal distribution, do they fall above? How many people, if we're assuming a normal distribution and they have a z-score of 1, do they fall above? So if they have a z-score of 1, they would fall right here. And we could look at this type of distribution, or even this type of distribution right here, and calculate all of these frequencies to the left of that z-score to tell you how many people they fall above. So in this example, if we're looking at a z-score of 1, we would take 0.1 plus 0.5 plus 1.7 plus 4.4, and so on and so on. And you can see how many people they're above based on their z-score. So it's a way of getting at pretty much the same concept as percentiles, kind of getting at the same concept of percentiles. We will talk about a much easier way to do that, but that's one way to think about z-scores conceptually. It's just how, what's your distance away from the mean? And if we're assuming a normal distribution, you can take that distance from the mean and estimate how many people you fall above or below in the data set. In general, what I want you to know, though, about z-scores, in general, okay, in general, and this is just a general rule of thumb, if you have a z-score of 1, that means you're slightly above average. If you have a z-score of 1, that means you're slightly above average. If you have a z-score of 2, let's change this. Once again, normal distribution. 1, slightly above average. 2, you're pretty strongly above average. If you're 2 standard deviations above the mean, if you have a z-score of 2, you're pretty strongly above average. That means you're better than 97.5? Yeah. That means you're better than 97.5 of people, because you're taking everything from this, and you're better than everyone from here down. So if you're 2 standard deviations above the mean, that means you're pretty solidly above average. If you're 3 standard deviations above the mean, that means you're extremely above average. And anything more than that, you're super, super extremely above average. So 1 is above average, 2 is pretty firmly or strongly above average, 3 is extremely strongly above average, And anything beyond that is just super spectacularly great above average. And the same goes for the other side. If you're -1 standard deviation from the mean, that means you're below average. That means you're somewhat below average. -2 is you're very below average. -3, extremely below average. And anything beyond -3, you're super duper incredibly below average. So hopefully you're not one of those people. Okay. Any questions about z-scores? Any comments about z-scores? Okay. All right, so I usually do a class activity where y'all get into groups and calculate variance and standard deviation. I don't want to do that because y'all aren't supposed to do group activities in person. So instead, I'm just going to go through really quickly because some students asked for this too. And just look at a quick data set, and I'm just going to calculate it myself. Some students wanted me to do a quick Excel how-to, so I'll just do that quickly. But if you have any questions, feel free to shout them out. I'm happy to show you anything in Excel as I'm doing it right here. So first, I'll pull up the data set. This is just the descriptive data set 1 from Canvas. So this is just descriptive data set 1 from Canvas. And whenever you're calculating or doing these basic analyses for test 1, for anything on test 1, you can get at it just by typing equal and then using the Excel command after that. So anything on test 1, you can just click on a blank empty open cell and type equal and then type in the command after that. Once it's to test 2, so test 2 will have a lot of things that you will have to use data analysis tab and Excel to do. But for test 1, anything can just be done with the equal and then the command. So if we want to calculate variance, if you ever do anything in Excel, you can just start by typing in what you think sounds correct, and then Excel will give you a bunch of options. You can hover your mouse, or you can click on it, and then it'll tell you what it does. So if you're ever on a test and you're thinking, oh, I need to calculate a variance, I think that begins with a V, like I don't know exactly what to do, you can just go ahead and start by typing in the V, and then seeing what Excel automatically populates with. So for this class, I'm perfectly fine if you just use the VAR command for variance. So if there's any question for anything in this class, and you just use the equal VAR command, I'm perfectly fine with that. So to calculate the variance of this variable right here, we would type in equals VAR, and then we would type in open parenthesis, and then we would type in open parenthesis. So equal VAR, and then open parenthesis. And then there's multiple ways you could get about doing what we need to do next. But one of the easiest is once we type that open parenthesis, we can just click on the data we want to calculate the variance for and drag all the way to the bottom. So just click and drag all the way to the bottom. So once again, we could just click and drag all the way to the bottom and release the click, and then close the parenthesis and hit enter. So once again, the formula was equals VAR, open parenthesis, click and drag the data that you want to calculate the variance for, and then close that parenthesis. And then we hit enter, and the variance for this data set is 1.41. The variance for this data set is 1.41. Okay. But as we talked about before, that's really hard to interpret. That's not in the unit of analysis of the original variable. So we probably want to do standard deviation. We probably want to calculate standard deviation. So the way we go about this is equal. And once again, we can just start by typing in what we think would be correct. So we can start by typing in ST. And we see that there's all these different ways to calculate standard deviation. And for this class, I'm always going to be happy if you just do the STDEV command. If you just use the STDEV command, I'm always going to count that correct. Always, always, always. So we're going to do equal STDEV, and then open parenthesis, and we're going to do the same thing. So equal STDEV, open parenthesis, and do the same thing. Click and drag that. So click and drag, and then what's the last thing I need to do? Yeah, close that parenthesis. Close that parenthesis. And hit enter, And that's our standard deviation. That is our standard deviation right there. It is 1.19. So that is how I would say if you had a test that asked you to calculate standard deviation and variance of something, that's how I would go about it. That's really quick, that's really easy. Just use the equal VAR command and the equal STDEV command. Any questions about that? Any comments about that? Okay. And then also, since someone asked me to go over it, if we wanted to do the mean, so Excel, the mean is actually the average command. So if you wanted to do the mean, I would just do equal average, open parenthesis, click and drag, close parenthesis. So whereas this was VAR, this is the average, and then equals. And then we want to do median, it would be MEDAN, open parenthesis, click and drag, close. This is median. And mode, equals MOD. Click and drag, and there is the mode. And if you remember from last class, I did note that if you have multiple modes in your data set, or you think there might be multiple modes, as there are this data set, that way does not give you multiple modes. That way will just return one mode. I think this one has multiple modes. Maybe I'm wrong about that. But either way, if you think your data set has multiple modes, there is a different way to calculate it to give you those multiple modes, and that is on mattchauer.com. So for that one, you will have to look at mattchauer.com. So. Okay, any questions about that? Any questions of how to calculate this in Excel? Any questions with variance, standard deviation, z-scores, anything like that? Okay. So then let's continue. All right, so that was the quick version of the activity. I wanted to do the variance and standard deviation. You can do z-scores on your own. I don't think we have enough time to talk about that in class today, but you can do the z-scores on your own. But those are the answers. So if you want practice on your own, we have the other data sets. You can pull up the PowerPoint, you can calculate it yourself, and then double check your answers with this slide on the PowerPoint. All right. So also the book talks about correlations very briefly in this chapter. So if you have the book, we will come back to that later. Correlations are extremely important. We will talk about correlations a lot in this class, but we will talk about them after the midterm. We will talk about correlations after the midterm. So for those who have the book, just skip the correlation part for now, because I prefer to teach it with the section on inferential statistics. Okay, so any questions about chapter 3? Any closing questions? Okay. So let's start chapter 4 before we take a break. So let's go ahead and start chapter 4. All right, so chapter 4 is all about probability. So we learned about charts and, we first learned about statistical terms, then we learned about charts and graphs, and then we learned about central tendency and dispersion. So now this chapter is going to talk about probability. So we're going really quickly, but we're just going to cruise on through. So this chapter talks about probability. So the reason why we need to know about probability is in the grander scheme of this class, all inferential statistics are also built upon the concept of probability. So while they're partially built upon the concept of descriptive statistics, all inferential statistics are also built on the concept of probability. And therefore, it's a good idea for us to learn about probability before learning inferential statistics. Also, probability is just a statistical concept, and there's going to be instances you're going to need to know probability. There's going to be instances that knowing probability will help you in business. So just knowing this basic statistical concept will help you in business too. Okay, so probability, just a good textbook definition, is it's a numerical value that measures or represents the likelihood an event occurs. So probability is a numerical value that measures or represents the likelihood an event occurs. So first, if I say something has a probability of 1, what does that mean? What does it mean if something has a probability of 1? Exactly, it will always happen. It will always happen. So if something has a probability of 1, it will always happen. And it has to If you say a probability of 1, it has to for sure always happen. For sure, for sure. What if I said something has a probability of 0? What if I said something has a probability of 0? It'll never happen. Ever, ever, ever. It will never happen. Never in a million, bajillion years would that ever happen. Okay, so therefore probability values range between 0 and 1. They cannot go below 0, they cannot go above 1. And 0 is it's impossible, whereas 1 is that it's definite. The microphone working? There you go. Okay. Upload it, compiles which okay. Thank you for okay. So yeah, so an experiment. Well, first off, any questions? And if you have any questions in chat, just feel free to throw it in there. Okay, so an experiment is a process that leads to one of several possible outcomes. In the context of probability, that could include things like rolling a dice. So things like rolling a dice could be an experiment. Because it's a process, rolling a dice, it could lead to one of several possible outcomes. So it could be you roll a 1, a 2, a 3, a 4, a 5, or a 6. So that could be an experiment, and those could lead to very different results. You could win $1 million, you could go bankrupt. Does anyone watch Community here? Anyone watch Community? One person? Okay, cool, one person. I just watched last night. They have an episode about rolling a dice, so I was just seeing if anyone here watches it. Okay, an experiment could also be flipping a coin. So flipping a coin is a process, flipping the coin, that leads to one of several possible outcomes, and several could be as small as 2. You could get heads or tails. So it's just a process that leads to one of several possible outcomes. Okay, so then a sample space is all possible outcomes from the experiment. So a sample space is all possible outcomes from the experiment. So in the context we've been using just now of rolling a dice, your sample space would be rolling a 1, rolling a 2, rolling a 3, rolling a 4, or rolling a 5 or a 6. And in the context of flipping a coin, a sample space is getting a heads or a tails, or getting a heads or a tails. So sample space is all possible outcomes of that experiment. And then the last definition I think I'm going to talk about is an event. So an event is the subset of the sample space, whereas a simple event is a single outcome of that sample space. A simple event is a single outcome of that sample space. So if we roll the dice, a simple event would be rolling a 1. So if we're talking about rolling a dice, a simple event could be rolling a 1, or maybe a 2. Exhaustive events includes all possible outcomes of that sample space. Exhaustive events include all possible outcomes of that sample space. So an exhaustive event is if we include every single simple event in that sample space. So exhaustive events would be if we include every single simple event of that sample space. So it could be if we're talking about rolling a dice, we include 1, we include 2, we include 3, we include 4, we include 5, and we include 6. And then the last one I want to talk about is mutually exclusive events. And they do not share any common outcomes. Mutually exclusive events do not share any common outcomes. So this would be, once again, rolling a dice. If you roll a 1, that means you cannot get a 2, 3, 4, 5, or 6. That means you cannot roll a 2, 3, 4, 5, or 6. So they are mutually exclusive. If we were to show it as a Venn diagram, I'll just draw right here, it would look like two circles that do not overlap whatsoever. It looks like two circles that do not overlap whatsoever. That if we rolled a 1, we could then not roll a 2. Or if we flip a coin and we get a heads, we could not also get a tails. All right, so those are the definitions I want us to use, or those are also the terms I want us to use. So when we're talking about probability, we're talking about experiments, sample spaces, and events. Okay, so the first type of probability I want to talk about is discrete random variables. The first type is discrete random variables. So discrete random variables assume a countable number of distinct values. So it's like we talked about before with discrete variables. So discrete variables have a countable number of values. So a discrete random variable has a countable number of distinct values that have associated probabilities. So that associated probabilities. So discrete random variables have a countable number of distinct values or distinct events, and they each have associated probabilities. So one could be rolling a dice, once again, or it could be something like determining whether someone is hired or fired, or I guess not hired. In this one, we have a distinct number of countable values, and it would be hired or not hired in this example. There's only two outcomes there. So we could count all the possible outcomes, and therefore it would be a discrete random variable. The other type we're going to talk about when talking about probability, which I believe is chapter 6, is a continuous random variable. A continuous random variable. So based on the definitions we've already talked about, what do y'all think a continuous random variable is? Someone say it again a bit louder. Yeah, so a continuous random variable can assume an uncountable number of distinct values within a range. Completely correct. So it can assume an uncountable number of distinct values within a range. So it could be something like the amount of time to complete a test. We could assign probability values to each observation within that. We could assume probability values to each range of observations within that. However, there's no exact number of countable events within that sample space. There's no exact countable numbers of events within that sample space. But we could say this student has a 10% chance of finishing the test between 10 and 20 minutes, but theoretically they could finish at 39 minutes and 29.1434 and so on seconds. So there's an infinite number of uncountable distinct values. So therefore we have to get that probability in a different way, depending if we're looking at continuous random variables or discrete random variables. If we're talking about discrete, we can look at each of those possible observations. We can say that this observation has a 10% chance, this one has a 20, this one has a 10, and so on and so on. We're talking about discrete. Whereas continuous, since we can't count all the possible different events, instead we have to assign probabilities to ranges. Instead, we have to assign probabilities to ranges of values. So once again, discrete, we assign probabilities to the exact events themselves. So rolling a 1, 2, 3, 4, so on and so on. Whereas continuous random variables, we assign probability values to ranges. So finishing within 0 to 10 minutes, 10 to 20 minutes, 20 to 30, and so on and so on. And that's the main difference between those two. Okay, so for this lecture, we'll be talking about discrete random variables. So this mainly covers chapter 4. This will cover some of chapter 5. And then continuous random variables is chapter 6. So discrete is mainly chapter 4 and some of chapter 5. Continuous is chapter 6. Okay. So before we get into all that, let's go ahead and take a 10-minute break. So let's take a 10-minute break, and let's meet back again at 7:15. Let's meet back again at 7:15.
Is it like a chapter? I got one of those. But it's like, yeah, I just said that. And I got all those wrong. I don't know what the heck I'm doing. I'm never not. Yeah, I like, yeah, I think. I literally don't know, because I answered it and I was like so confident that I got it right, and then I messed it up. And I don't have another, like, check my mark. Wait, here, let me get to my next. It's only 5 questions. Okay. You can, I think you can, yeah. Okay, so I have one of them, but there's like a weekly class that's from my Thursdays, and like, yeah. Yeah. So I didn't check my work and I took those subjects that I knew I did wrong. I started off thinking, and then I guess that. But if I don't have them, so I was doing
What number is that, chapter 2 or 1?
it's number 3 on chapter 1.
I don't know.
It's like that huge graph where you have to like put in all the data sheet.
Yeah. If you don't put negative signs, it's going to come wrong.
Yeah. Well, I put the print rate.
Yeah, you just, like, don't do that in the front line.
I know, I did do that though. Yeah,
You gotta make sure they're in the right order too. Exactly.
there's also don't way that all the all numbers the same. Like how they're all the same, how they're like there's just like that. If you have like someone that you're getting them right, and like it's the same number. That's probably that's not
That's just good. That's just
not the
good. Hey, did you notice them? No, that's why.
I know. I have to check. I just don't get how to get, like, I don't even understand how to do it. Okay, so for every number that you come out, like, yeah, so as it goes down, it's gonna like, so like, that's what I'm saying, number 2, they're just like, double pronouncing. That's just like, so I have to just like, let me see where they're okay, just a second. Okay, so it's just it doesn't all have a part of it, that's like rates that have $1,000 per year. So there's no way to so
We also got the variance.
would have thought that would have been. I know, I'm so nervous because like, you didn't like check my work. Yeah. Okay. So it's like, yeah. Not all of them are very, oh, come on down. So look, I got like this part right, and I got all these reports. For every single question, you're not gonna always have time to do it. You're not gonna know it.
What you need to do is go back to the job section. When you read the screen, how to do this. I take off and do it. That helps me figure it out. I had to do it.
Did you run it? And then I found out. So for this study, one just for my knowledge. Yeah. So what the things I do, if I'm gonna be negative.
It's not gonna be negative, it's only negative. It's positive.
So if I take these parentheses off, it's right. Yes.
You have to do it. And you also, we have different conversations. I didn't know that.
But, okay,
Okay,
so,
it doesn't matter.
okay, well, then, I mean, so, if I put this, for instance, outside of parentheses. So, do I put a negative? I put a cash, and then positive in the.
Once you make a sale, that's when you do that.
So it looks more like that. All these.
Yeah, it should all match the return on target should match. Yeah, the return on target should match that.
There's not very much.
Yeah, it depends on what it is. If it's machine call, it's different.
Yes. Did you take? Yeah.
First case.
I did play case study already. We did that. Yeah, you had to say whether or not you thought it was, the sales would be flat. Wait, oh, so you're watching this, okay. No, one is easy. Two isn't bad either. I got those wrong, those three.
How many tries did you do? Oh, wow. Okay.
Well, no, you get plenty of try, well, you get one check mark, you know, so you have to check your work once. Once you submit it, you're done. Yeah.
It says unlimited, once you submit it, a lot of them.
Yeah. It lies. Do you already know all Oh my God. Yeah. That's all that's in my book. Okay, well, that's, okay. I feel like I just have to keep doing that.
I'm trying to eliminate my own self.
I have way too many.
Yeah.
I want to.
That's what I wrote.
I kept referring to that first motivation. So then you kind of took this. That's a good strategy. I know, right? Yeah. Yeah, that's perfect. I'm already on here, so I may as well.
Yes.
Later.
It's going to get rolled into chapter 4. So today we're mainly going to do 4 and 6, and then like some of faster. Yep. Okay, we good to start the second half of class? We good in the front? We good in the back? All right. We good in the front over here? And are we good in the back over here? Awesome. Let's go ahead and continue. Let's cruise on through until 8:30, I guess. We'll see. All right. So we're talking about probability. We're talking about discrete random variables, rolling a dice, flipping a coin. You want to think of any examples other than rolling a dice and flipping a coin?
Cards.
Oh, that's a good one. Yeah, cards. Yeah, so cards is 1 in 52 chance. So thank y'all for that. Good job with that. Yeah, rolling a dice, flipping a coin, throwing cards. Yeah. Okay. So we're talking about probability and we're talking about discrete probability. we can make a probability distribution. We can make a probability distribution. And a probability distribution just gives you all possible events in your sample space, and it gives you the probability for each of those events. So it gives you each of the events in your sample space, and it gives you the probability of each of those events. So with rolling a dice, we see right here, we have each of the probabilities. We're rolling a 1 through a 6, and each of those have an equal chance of occurring. In this example, each of those have an equal chance of occurring. So we have a roughly 17% chance for each of those options. So that's a probability distribution on the top. The bottom one is a cumulative probability distribution. The bottom one is a cumulative probability distribution. So from looking at that, can anyone tell me what a cumulative probability distribution is? So they eventually equal to 1, yes. So the last one equals to 1. So what does that mean?
That's the total amount.
So each option added up. I think you are close. Sorry, say it again.
Finite.
It is finite. You are in the ballpark. Is the first one is the probability of the first one. The second one is the probability of the first or the second one. So you see the probability of the first one is just the probability of rolling a 1. Then the next one's the probability of a 1 or a 2. The third one's the probability of a 1, a 2, or a 3, 4, 1, 2, 3, 4, and so on and so on. So a probability distribution function just gives you each independent event and a probability for each. The cumulative probability distribution gives you the probability of the event as well as everything else that came before it. So the event as well as everything else that came before it. So the difference between those is a probability distribution. It's just the probability of each of the discrete events. Whereas a cumulative probability distribution is the probability of each event and everything that came before it in the distribution. So that's the difference between those two. So in the previous example and the ones we've been using, they're called a discrete uniform distribution. So we've been talking about discrete distributions. A discrete uniform distribution is a particular type of discrete distribution. And that's a distribution where the probability for each outcome is the same. The probability for each outcome is the same. So with rolling a dice, the chance of rolling a 1 is equal to a 2 is equal to a 3, and so on and so on. So with rolling a dice, that is a discrete uniform distribution because we have 6 different options. 1 equals 2 equals 3 equals 4 equals 5 and equals 6. And that's why that's a discrete uniform distribution, because the probability of each is equal throughout. Same with flipping a coin, same with a deck of cards. I know I should know this. How many cards are in a deck? 52, okay, so I was right. So we had 52. I could write that out on the board where 1 equals 2 equals 3, so on and so on. And with flipping a coin, I can write that 1 equals 2. So in each of those examples, each outcome has the same probability, so therefore they are discrete uniform distributions. And this is what it might look like visually. If we were to make a probability graph, we see that the chance of rolling a 1 is the same chance as rolling a 2, 3, 4, 5, and 6, so on and so on. So when you think of a discrete uniform distribution, a discrete uniform probability distribution, think of a bar graph because we have separate possible outcomes, and each of the bars have the same height. And each of the bars have the same height because they have the same probability. Okay. So also, as someone already pointed out over here, whenever we're looking at a distribution like this, the combined likelihood of all the possible events is 1. The combined likelihood of all possible events is 1. So if we're looking at something like participating in the Olympics, we might say that there are 4 different options. So this is a discrete distribution. And it's not uniform, as we'll see. It's not uniform, but there are just 4 options. So it's gold, silver, bronze, or no medal at all. Then we can assign probabilities to those. So as we see, the one on the left, it adds up to 1. But the one on the right does not add up to 1. So what does that mean about the one on the right? It could be incorrect. It certainly could be incorrect. That maybe the probabilities are wrong. It is possible the probabilities are wrong. What else could it mean? Yeah, that's perfect. Yep, it's not exhaustive. It's not exhaustive. But if you see something like this, it could mean that an option is missing. Maybe the Olympics added a platinum finisher or something like that. So if you see something like this, it could be that the probabilities are wrong, or maybe it's not exhaustive, but there might be some possibilities that are missing. So think about that when you think about probabilities. When someone gives you those certain probabilities of something happening, think about whether those probabilities are correct, but also think about whether there's some options that are missing, whether there's some options that are absent. Okay. Also, other concepts we should know about this. There's the concept of subjective probability. So subjective probability All right, can y'all hear me now? Yep. I don't know, I need to look in to see why that works. I will, can someone send me with a laptop, send me an email right now that just says contact IT about audio, so I'll remember. You got that? Thank you, perfect. Okay, I'll deal with that before next class. Okay. So with subjective probability, it's when, if a student throws a paper ball, gets in the trash can, and I yell out, there's a 0.01% chance of it happening. That's just based on my own subjective estimation. That's based on my own personal estimation. So subjective probability is based on your personal estimation, you're based on your intuition, and it doesn't have empirical observations behind it. It's based on intuition. On the other hand, empirical probability is when probability values are assigned based on repeated observations. So empirical probability is when probability values are assigned based on repeated observations. So if anyone ever says, based on our prior observations, we might have a 75% chance of meeting our quota for the month, that's empirical probability. In the prior example where I gave Olympic medal finishes, that was empirical probability, because I could look at all the history of the Olympics, everyone who's ever competed, and they get probabilities from based on their finishes in the races, whatever they did. One thing I want to note about this is typically when we're talking about statistics, we of course prefer empirical probability, because we're people of science, we like data, we like numbers, we like there to be support for what we're doing. But subjective probability can be useful. Subjective probability can be useful. Often in instances where we might not have an opportunity to get empirical probability. So there might be some instances we might not have the opportunity to get empirical probability. Can anyone think of any examples we might have to resort to subjective probability? Anyone have any examples?
Maybe like it's a little basketball tournament.
Okay, expand on that.
Because, I mean, you can't really base it, based on what team was. That doesn't mean not anything good. I don't know.
Yeah, it depends on how you look at it. That could work, yeah. As we could look at empirical and say like, oh, over time, number one seeds have, we've also 16 seeds once. But when it comes to that exact matchup might have never happened before. So yeah, that could go either way. So certainly, yeah. Any other examples anyone wants to give? Okay. One thing we see often in business is something like major company decisions. We would like to have empirical probability. So things like, let's talk about the business school here in the Mitchell College of Business. We recently decided to add an additional PhD program. We would really love to have empirical probability to show that, based on repeated observations, if we started this program instead of this one, we would have a 75% chance of being successful, whereas this one only has a 25% chance. We would love to have empirical probability for that. But that data doesn't exist. We don't have that data. So instead, we didn't have to, but we chose to pay a professor a lot of money, who's a renowned figure in the field, who we think has a very strong intuition about what would be successful, and had them start the program and say, all right, which one do you think we should do? So often with major business decisions, we don't have access to data. We don't have access to empirical probability. So we instead have to rely on subjective probability. And that's why certain CEOs can make a ton of money, because they're the only ones who can make somewhat close estimates of that probability, of accurate subjective probability. Any questions on probability so far? Yeah. Yeah, so it depends on how you look at it. That's kind of what we're talking about over here. In some ways, you could try to argue it is empirical, because in some ways you could try to argue that, oh, we do have prior data, we could generalize that, but this gets later in the semester. It depends on how much you're willing to generalize. Like with the NCAA tournament, if you're willing to generalize that this particular game between a 1 seed and a 16 seed can generalize all the prior 1 versus 16 seeds, we could say that's empirical probability. But if you're only comfortable saying, no, it has to be about these particular people and these particular teams, then you would have to say it's subjective. Then you would have to say it's subjective. So, did that answer your question? Okay. Any other questions? And that was a good question. Good. Yes?
Can you give another example for subjective?
For subjective probability?
A useful one that you would say, another example.
Another one, not so PhD, we could say it was CEOs. Really anywhere in a company. What? I think we talked about the example I keep on thinking of is your homework assignment, so I'm trying not to use that one.
Election be subjective probability?
Okay, it could be, yeah. Yeah, is that what you were going to say something? Okay, expand on that. Yeah. Yeah, that could be subjective, and that goes along also with how much you're willing to generalize. So we could have data on prior similar applicants. So if we want to generalize and say, all right, those similar people generalize to this person, we could say that's empirical. But we don't have exact data on that exact person. So then if we're not comfortable with those generalizations, yeah, then it would have to be subjective. Then we would have to say that based on our estimation, what we do know about that person, maybe their personality, maybe where they worked at before, we can have a percentage that we throw out there. So that's a good example. Both of those were good examples. So, did that help at all? Yes. Okay, good. Very good. Any other questions, comments? Okay. So we will talk about, maybe as soon as Wednesday, the concept of generalization a lot more. We will talk about that a lot more, probably on Wednesday. Okay. So this would be an example of, empirical probability. So this would be an example of how we could get empirical probability for a sample or a population. So in this example, I believe, this is 400 students. So we could collect a sample of 400 students, let's say from all across campus, and we could ask them their ages. And we could just make a simple chart like this, where we have ages of 18 and below, 19, 20, 21, 22, 23, and 24 and above. So out of those 400 students, we put them each into their respective categories. And then for each of those categories, we just take the number of observations and divide it by the total sample size. And that gives us the probability for those categories. That gives us the likelihood of observing those categories, or the probability. So for the very first one, we only had 7 students that were 18 or younger. So we take 7 divided by 400, and that's 0.0175. So based on this, we could get an empirical probability estimate. That in our sample across South Alabama, if we were to get a random student, we would have a roughly 2% chance of them being 18 or younger. Same, let's do it real quick with 19. In our sample of 400 students from all across campus, we might have 47 that are 19. So we take 47 divided by the total number of our sample size, which is 400. 47 divided by 400 is roughly 12. So we can get an empirical probability estimate, and that would mean that if we were to take a random student on campus, there would be a roughly 12% chance that they would be 19. Does that make sense? Okay, and that's how we can go about actually getting our empirical probability estimates. Is we can get a sample from many observations, in this case 400, and then calculate the frequencies based on that sample. And that's how we get an empirical probability estimate. And once again, like I said before, this is what we would prefer to have in business. This is what we would love to have in industry, but we often aren't able to do that. We often don't have the time or the resources to get a sample like that, and that's why we do have to resort to subjective probability so often, much more often than we would like. Okay, so this always comes up every semester. I want to talk about this now. Okay, yeah, so this comes up every semester. So usually around now I have a student ask, all right, so when we get a sample like that, how do we know that that works? How do we know that that represents the population? How do we know that your 400 students, like, why would that apply anywhere else other than those 400 students you collected? And that's why we should talk about the law of large numbers. That's why we should talk about the law of large numbers. So can anyone tell me, just in plain speak, what is the law of large numbers?
The more data you have, the more likely it is that.
Yeah, that's one way to put it. Yeah, it's pretty much the more data you have, the more likely it is that you're correct. So the textbook definition is when, or a textbook definition is that the number of observations reach a large amount, the empirical probability approaches the actual probability. So once again, once the number of observations reaches a large amount, the empirical probability approaches the actual probability. So pretty much once your sample size gets large enough, the probabilities that you're able to empirically estimate roughly approach the actual probabilities.
That large number.
It is, but it's also much lower than you would think, and we will talk about that. If I don't bring that up in like 3 minutes, bring it up again. So in this prior example, if we assume that 400 students was large enough, then yeah, then maybe these observed frequencies are pretty close to the actual frequencies. Maybe these observed frequencies are pretty close to these actual frequencies. That if 400 approaches the large number cutoff for the law of large numbers, these could be close to the actual frequencies. And that's a really central idea behind all statistics. And this applies to inferential statistics. Often when we get a sample and we calculate a correlation, we assume the correlation of that sample applies to the population. We assume the correlation of that sample applies to the population. And if we have a small sample size, that might not work. That might not apply. That the correlation in our sample might not apply to our population if our sample size is small. But according to the law of large numbers, if our sample size is large enough, even for things like correlations, regression, t-test, ANOVA, the results we get for our sample approaches the actual probability or the actual results of the population. So this does apply for anything we'll talk about all throughout the semester in this course. There is a ton of research, you can teach a whole class just on the law of large numbers. The short of it is, yeah, it seems to work. It seems to be accurate. There's book-long statistical proofs supporting the law of large numbers. And yeah, it seems to be an appropriate law. However, one thing for us, for our purposes, is the question of what is big enough? What is big enough? So if we're talking about students on campus, if we're wanting to collect a sample that we think would be big enough to generalize to all students on campus, do y'all think 20 would be big enough? Probably not. Probably not. What about 200? Would 200 be big enough? What do y'all think? Mostly no's. All right, so no's. We're wanting, and how many students do we have on campus? It's about 14,000. 13,500? Yeah, so about 13,500. So do y'all think 2,000 would be big enough? One person says yes. 2 people say yes. One person shaking their head maybe. And then, of course, if we had 20,000, of course, that would be big enough. The one thing I want to say about this is, like I said, it's often smaller than you think it would be. There's statistical calculators you can have where you can type in what you think your population size is. So if we're only interested in students on South Alabama, we could type in, oh, we're interested in a population of about 13,500 people. And it will tell you what your sample size needs to be representative of that population. If in those calculators you type in your population as something like 1 billion people, it claims that to reach that cutoff for the law of large numbers, you might need as few as 484 people. That tends to be where it plateaus at. It tends to plateau around 484. So for a lot of social sciences, if you get 500 participants, if you have a sample size of 500, then you can generalize to your broader population and and a lot of people will not call you out. People will be less critical of that. So based on these statistical proofs, based on these calculations, people have found that roughly a sample size of 500, that's often big enough for generalization purposes. I will say that that assumes you're getting a perfectly complete random sample. That assumes there's no biases in your sampling process. That assumes that your population is very homogeneous. That assumes there's not subsets in your population. If there are, you're equally sampling from them. So can you all tell me, does that usually apply in practice? Usually not. Yeah, there's usually subsets in your population. You're usually not doing a perfect job sampling. So often these calculators are not 100% accurate. Usually you do need a sample size. You want to be 100% certain, larger than 500. But if we're perfect, that's what we would be shooting for. So, okay. So in short, that's why a lot of our statistics regarding samples can apply to populations, is because of this law of large numbers, and saying that once we get enough participants, our empirical probability approaches our actual probability. So if you have a sufficiently large sample size, it does indeed represent the population. And there's the sample size calculator if you want to look at it on your own. So if you're ever interested in studying something like South Alabama students, and you want to see, well, how many students can y'all hear me now? All right, thank you all very much. Okay. Other rules to remember about probability, and once again, this plays more once we get into inferential statistics. The first one is the complement rule. So the complement rule simply tells us the probability of an event not occurring is 1 minus the probability of the event occurring. So the probability of an event not occurring is 1 minus the probability of the event occurring. How do I want to do this? So the complement rule is that 1 minus the event occurring equals I'll just okay, so the complement rule is just simply the probability of an event not occurring is 1 minus the probability of an event occurring. So the reason why that works is, as you all know, the entire range of possible probabilities we can have sums up to 1. So the entire range of probabilities that we have sums up to 1. So 1 minus the probability of the event occurring is just the opposite. 1 minus the probability of the event occurring is just the opposite. So therefore, the probability of an event not occurring, which is the opposite of it occurring, is 1 minus the probability of the event occurring. So if we roll the dice, so depending on the complement rule, if we wanted to see what would be the likelihood of not rolling a 1, what would be the likelihood of not rolling a 1? So we know that the complement rule says the probability of something not occurring is 1 minus the probability of it occurring. Y'all remember what the rough approximation probability of a dice roll is? Yeah, 1.67 or 0.167. There you go. So the complement rule says that we take 1 minus the probability of the event occurring to see the probability of it not occurring. So in this instance, so let's just make it simple. Let's just make it rounded up, 0.17. So that means we have roughly an 83% chance of not rolling a 1. So to use the complement rule, if I had on a test, what's the probability of not rolling a 1 on a dice? Assuming that we have a 0.17% chance of rolling a 1, that's how you would find that out. You would say I'm using the complement rule. I just take 1 minus 0.17, and that's 0.82. The next rule you should use or know is the addition rule. So the addition rule is the probability that A or B occurs is the probability of A plus the probability of B minus the probability of both A and B occurring. So once again, it's the probability that A or B occurs is the probability of A plus the probability of B minus the probability of both A and B occurring. So can anyone tell me why we subtract the probability of both A and B occurring here? Yeah, yep, because you would otherwise count it twice. So let me erase this. Okay, because you would otherwise count it twice. And the way to visualize this is, let's say we have two events. We have A and we have B. This overlap is both A and B occurring. So therefore, if we were to take these probabilities, and we wanted to see what is the probability of A or B, we want to see the probability of A or B, it would be the probability of A plus the probability of B minus the probability of both A and B occurring. So the reason why we subtract that A times B, which is this part right here, is because if we first take the probability of A, we're taking everything in this circle. If we first take the probability of A, we're taking everything in this circle. If we take the probability of B, we're taking everything in this circle. We're taking everything in this circle. So if we were just to do that and leave it at that, this part right here would be included both in A as well as in B. So this part right here would be included in both A as well as B. However, in this one, the addition rule, we're interested in A or B occurring. So therefore, we don't want to double count this. So therefore, we do not want to double count this. So therefore, we take A plus B and minus A times B. Minus A times B to account for this overlap right here. Because we only want to count it once. If we're counting it in both A and B, we have to subtract it once. So, does that make sense? Okay, good. Any questions about that? Okay. Another important note about the addition rule is if mutually exclusive, the probability of A and B occurring is 0. That's what we drew before. If they're mutually exclusive, the Venn diagram looks like that. If they're mutually exclusive, the Venn diagram looks like that. So if I were to say, let's give this example. We're looking at an employee we're thinking about hiring. The options are hire, not hire, and wait list. Those options are mutually exclusive. Those options are mutually exclusive because you cannot hire and not hire someone. You cannot hire and waitlist someone. You cannot not hire and waitlist someone. So these options are mutually exclusive. So therefore, this formula right here, and let's make it simple. Let's just kick out the waitlist part. So therefore, if they're mutually exclusive, what happens to this formula right here? If they're mutually exclusive. Say it again. Yeah, it would just be A plus B. And why is that? Yep, because you can have A and B together. Or another way to put that is that A times B is 0. That's another way to put it. But because there's no overlap here, the probability of both of them occurring is 0. So you can either think of it as it's just A plus B if it's mutually exclusive, or it's A plus B and then this AB is still there, it's just minus 0 if they're mutually exclusive, if they're this right here. Okay. Any questions about that part? Any questions about anything we've covered? Going once, going twice. All right. All right. Another one we should talk about is the multiplication rule. And I know we're going over these quickly, but we'll cover these throughout the semester. They come up again when we're talking about differential statistics and the such. So another one is the multiplication rule. So the multiplication rule is the probability that A and B both occur with the probability that A occurs multiplied by the probability that B occurs given A. So the probability that A and B both occur is the probability that A occurs multiplied by the probability that B occurs given A. And for the purposes of this class, if I'm going to give you a question about the multiplication rule, we're going to assume the events are independent, just to make it easy for y'all. We are going to assume the events are independent, just to make it easy. And if those events are indeed independent, The multiplication rule is just the probability of A occurring multiplied by the probability of B occurring. The multiplication rule, if they're independent, is just the probability of A times the probability of B. And one way to look at this, for this one, is the addition rule. So this is the multiplication rule, and this is just if they're independent, A times B. If we were to think about it as a Venn diagram, it's just this part of overlap right here, which is what's the chance of both A and B occurring. It's a question for the class. Let's say I wanted to figure out what's the probability of flipping 2 coins and getting 2 heads. How would I figure that out using the multiplication rule? So flipping 2 coins, I want to know the probability of getting 2 heads. What would that look like if I wanted to use the multiplication rule to figure out the probability of getting 2 heads? Yep, exactly. Yep. We would just take, let's do it right here, 0.5 and 0.5. So we know the probability of getting 1 heads is 0.5. The probability of getting the second heads is also 0.5. So therefore, the probability of getting 2 heads is 0.5 times 0.5. That's 0.25. So using the multiplication rule, we can figure out that the probability of getting 2 heads is 0.25. So it's just taking the probability of A, getting the first heads, times the probability of B, getting the second heads, and that is 0.25. We can do the same thing for rolling the dice, something like 0.17 times 0.17, and so on and so on. Actually, it's a little bit more complicated for rolling dice, but we'll know that. Okay. Any questions or comments about that?
So we also know do the benefits?
Yeah, we are, for the purposes, if there's anything about the multiplication rule, we will not talk about dependent events. We're just going to assume they're independent. Yep. And all the questions will say assuming that they're independent, dot, 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 dot. Yep, good question. Yep. Any other questions? All right. Sometimes this can be confusing based on your frame of reference. So for the first one, the question is, for a coin flip, what's the probability of flipping a heads? So what is the probability of getting a heads? Yeah, 0.5. And then what's the probability of getting 2 heads? 0.25. However, let's say we flipped a coin and we got a heads. What's the probability of then getting a second heads? Yeah, 0.5. And that's because it depends on our reference. It's because these are independent events, and the prior event doesn't affect the future event. So if we're just talking about the probability of flipping 2 heads before both of them occur, yeah, the chance is 0.25. But then if we get 1 heads, and then we haven't flipped the second coin yet, and then we say, well, what's the chance of us getting the second heads? Suddenly it's just a 50-50 chance. It's because that first event that's already occurred doesn't impact the second event. So once again, these probabilities, it does depend on your frame of reference. It does depend on when you're asking about the question. So if you're asking about flipping 2 heads before both of them have been flipped, versus about flipping the second head after the first one has been flipped, those probabilities will be different. Okay. Other things we should know about discrete probability. So first, all contingency tables are a good way to visually show the probabilities and frequencies of the 2 variables. So this might be if we have 2 different variables and we want to see how the probabilities and the events of them intersect. So let's say, once again, we're going back to our sample of college students. Let's say we have 600 of them, and we're looking at the probabilities of both age and class outcome, if they're in a class, and how they intersect. So contingency tables are a good way to show the frequencies and probabilities of 2 variables, so both variables independently, as well as how they intersect. So we could look at a contingency table and see with this one, we have age under 20 over 20. And let's say for simplicity's sake, all 600 of these people are in the same class. And we want to see, well, how do those variables relate in regards to pass, fail, or getting an incomplete in that class. So how we would do that is we would make a contingency table where we would have each possible combination in the squares right here. So we have under 20 pass, under 20 fail, under 20 incomplete, and then we have over 20 pass, over 20 fail, over 20 incomplete. So we would have each possible combination of those. And we would just take the 600 people and put them in the cell that they represent. So as you see in this, we have 174 people who are under 20 and passed the class. We had 132 students who are under 20 and failed the class, and so on and so on. So that's what we do for those 6 cells right there, is we just take the direct observations and put them into cells. But then for these outside cells, we have to add up the rows and columns. So this right here simply adds up the row right here, and we see that we have a total of 396 students who are under 20. This right here, we add up the row, and we see we have 204 students who are over 20. And we can do the same thing for the columns. 228 passed, 204 failed, and then 168 had incomplete. So one reason why I might want to do this, to make this frequency contingency table at the top, is then to make the probability contingency table at the bottom. We then make the contingency probability table at the bottom. And the way we do that is we would take each of these cells and divide by the total sample size. So like we were talking about before with the frequency tables, the probability tables, same concept. It's just now we take the sample size, divide each of these by the sample size. And from here we can see 174 divided by 600 is 0.29. So based on our sample of 600 students, what does that tell us? Yeah, expand it out. Yeah. So yeah. So that would mean that 29% of our sample were students under 20 that passed. So this right here means that 29% of our sample were students under 20 that passed. Right here, 22% of our sample were students under 20 that failed, and so on and so on, until we get to something like, let's look over here. This would mean that 66% of our sample were under the age of 20, irrespective of the class outcome. Over here, 34% of our sample were over 20, irrespective of class outcome. Down here, 38% of our class passed, 34% failed, and 28% got incompletes. So once again, just looking at how we can take observation based on a sample, and we can make probability estimates, but in this case, it's looking at how 2 variables intersect. In this case, it's looking at how 2 variables intersect. I think that's all I have to say about that. Do y'all have any questions about that, comments about that? Okay. All right, so then to finish this chapter on probability, the book includes Bayes' theorem in chapter 4. If you have the book, just cross out everything about Bayes' theorem. That is, we are not going to talk about that in this class. Bayes' theorem is something you can take an entire graduate seminar or multiple graduate seminars on. So there's no reason to really just touch upon it without talking about it more in depth. And also, as I mentioned, chapter 5 talks about discrete probability functions in more detail. So that might be important to some. We included some of chapter 5 in the lecture we just covered, but not all of it. So if you're really interested in these discrete probability functions, go back, take a look at chapter 5 in your textbook. But what we covered today in class is the extent we're going to talk about it for the purposes of this class. So long story short, what we talked about in class today is all you need to know about discrete probability functions for the purposes of the test. But if you want to know more, the textbook is there. Okay, so that's all for chapter 4 and 5. Any questions? Okay. So give me 1 sec. All right, how's y'all's energy going? Do y'all want to keep going, or do y'all want to stop there for today? I like your honesty. All right, raise your hand if you want to stop. Be honest with me. Raise your hand if you want to keep going. All right, well, I think it was something like 4 versus 2, so I think y'all are too tired to even vote. So let's go ahead and stop there for today. We do have a day that I have scheduled to catch up on material, so we're good. I'm tired too. And I want to get the audio fixed because I think it's going to cut out on us in a few more minutes. So thank you all for hanging in there with me today. I know probability is not the most exciting thing ever, but it builds to more exciting things. It will build to more exciting things. So thank you all for hanging in there with me. I will see you all on Zoom on